Hi, everyone. I want to start chapter 11 in our textbook, which discusses electronic spectra of transition metal complexes. But I'm going to start this off with a few slides that are just sort of focused on why do we actually see electronic spectra, or I should say absorption spectra, in the UV, vis, and near infrared parts of the spectrum. So let's remember a couple of things. So when you have transitions in molecules that are in the visible, the color you perceive of what you're seeing in solution is a result of the transmission of light, of typically of white light, through that sample, which means it's absorbing color that's complementary to what's being transmitted. So an example of this would be if you actually perceive blue color from a solution, chances are that that's resulting from the fact that you're absorbing orange, much like the color of the pen I'm using. And ultimately, what we do is we now can have a metric for where something absorbs light, or where a molecule or material absorbs light. And then we're able to identify that that's representing an energy difference between a ground state and an excited state. And then that's simply just a consequence of Planck's equation, where the energy difference between the ground and excited state is just the energy of the photon in frequency times Planck's constant, h. If we put that in terms of wavelength, we know that that's also the same as saying delta E is equal to hc over lambda, and lambda here is then in nanometers. And then, of course, when you measure something on a spectrometer, you're really measuring wavelengths. And then ultimately, for our purposes, is you want to relate that back to energy. And you can kind of see what will happen in inorganic spectroscopy. We use wave numbers or reciprocal centimeters very often. And the interconversion between nanometers and wave numbers is basically if you effectively take 1 over the wavelength times 10 to the 7th, that will complete that conversion. But then just as a guide, I have a bunch of information up here about what species typically, what they usually are, the colors that are observed, and then like where the light's absorbed in this table up top. But normally, most of the transition metal compounds we actually look at are going to actually have colors that are primarily in the visible, and then those are corresponding to transitions that are easy to measure in terms of wavelengths, and then of course we can relate that to the energy difference between the ground and excited state. So really, UV, vis, near IR spectroscopy is a great probe for electronic structure. So a little more detail about this. Let's ignore two-photon absorption completely, because that's another specialized topic for my photochemistry course. But what this is illustrating here is if you have a sample that you're really perceiving as orange, its complementary color is blue, and you can kind of see what's happening. Blue is primarily being absorbed in this sample, and then the rest of the photons in it are being transmitted. That's what this is intended to show. And then the absorbance you measure follows what's called the Beer-Lambert law, but it's also the log of the incident light intensity divided by that that passes through. So I0 is what's incident on the sample, I is what passes through. And that's related to the molar extinction coefficient times the path length times the concentration of the sample. So the typical way that you evaluate extinction coefficients is you use a constant path length cell. Typically it's 1 centimeter. And then you can systematically change the concentration of the sample, which then changes the absorbance. And then the absorbance is then directly proportional to what the extinction coefficient is. and that is the way to get at that value. And since the extinction coefficient is really related to a numerical value that's inherent for any given molecule or material, that then relates to how allowed the transition is. And typically what you'll see is that there's going to be selection rules that then follow that process. So you have to kind of get a good sense of what are the magnitudes of extinction coefficients that are observed in typical types of compounds, and then how does that relate to the allowedness of the transition. And when you're doing this in the typical photochemistry sense, you can actually excite from the ground state to the lowest excited state, which is termed S1, which just means it's a singlet excited state. So if you started out with a singlet ground state, as you do there, and then you basically make a singlet excited state, what you would then have is one of the electrons would be spin up, the other one would be spin down, and that's now the singlet excited state, but they differ in energy by the absorption of the photon. And then you can actually promote molecules to upper excited states. So if you didn't populate S1 initially, we can just get rid of that. And then we say, well, we can do a transition from S0 to S2. And then that occurs at higher energy, but it also illustrates the fact that most compounds don't just exhibit one single electronic absorption band, they have multiple absorption bands. And then this is the example that was up here is just remember if the absorbance of a sample is 1 at the peak wavelength and the intensity is basically 0.1 of that times I0. So that basically is telling you you're transmitting 10% of the incident light and it's absorbing 90% at the wavelength that you're observing. So it just gives you an idea of the complementary processes that go on between absorption and transmission. So whatever is absorbed is, whatever is not absorbed is transmitted, and whatever is not transmitted ends up being absorbed. So just to round out the discussion a little bit, to think about some of the fundamental selection rules that are inherent in transition metal complexes is that transitions between orbitals with the same parity, and parity for us is effectively meaning that if you have, for example, a T2G to EG transition, the fact that they're both the same parity or they're both Garada is telling you that that transition is forbidden based on what's called the Laporte selection rule. So you effectively cannot have transitions between orbitals that have the same parity. That's what that really means. So you're not allowed to do any transitions between Garada and Garada, or ungarada and ungarada, and of course those really only only pertain to the octahedral point group in our initial discussions, because that's where we see Garada and ungarada symmetry as a result of the fact that the molecule has an inversion center or possesses an inversion center. But the other thing is that if you have transitions between G and U, those are actually allowed by the Laporte selection rule. Another selection rule, which is very common, and this is by far the most prohibitive, when something is spin forbidden, that is incredibly prohibited. And spin selection really prevents a lot of things from a lot of transitions from happening in the first place. So what do I mean by spin forbidden? Well, basically it's the spin multiplicity of the ground state versus the spin multiplicity of the excited state. If they're different, that makes the transition completely spin forbidden. So for examples of this would be if we had some of these ligand field term symbols, which we haven't discussed yet. If you have a quartet A2, which is this, to a doublet A2, that's absolutely spin forbidden because the spin multiplicity changes in the transition. Whereas if you pick the second transition here, where you see it's a quartet A2 and a quartet T1, The superscripts are indicating those are the spin multiplicities. The spin multiplicities are quartets. The spin multiplicities being quartets tells you that that's a spin allowed transition. And remember all of these terms. If you have a quartet, it basically means that you have, for example, 3 unpaired electrons in some set of orbitals. That gives you the quartet spin multiplicity. Doublet spin multiplicity would be, for an example, if you just have a lone electron that is spin up. So you can kind of see there. If you have 2 spin up and 1 spin down electrons, that is formally going to give you a doublet state, whereas this will give you a quartet. And remember, spin multiplicity in the simplest form is really the number of unpaired electrons plus 1 gives you this answer. So obviously here, 1 plus 1 gives you 2, which is a doublet. And then down here, 3 plus 1 is 4. That gives you a quartet. Now, what does this forbiddenness mean? Well, it tells you really that fully allowed transitions have very large extinction coefficients. And for example, a pi to pi star transition has effectively spin parity changes because pi orbitals, as you all know, are ungarada. Pi star orbitals are actually garada, and you see the U to G working in your favor there. So that transition is completely allowed by the Laporte rule. As long as the spin is conserved, that transition would be fully allowed. But in transition metal complexes, we run into this problem. We have D to D transitions. So they can be spin allowed, but they're going to be Laporte forbidden. But it doesn't mean, just because they're forbidden doesn't mean you don't see them. They are completely observable. And why are they observable? And I'll show you this later, but this couples, when the transition couples to a vibration that distorts the molecule away from the octahedral point group, that actually makes the transition allowed in part, because during the vibration event, the molecule's absorbing light, and then that is necessarily going to give you an observable absorption band. In other cases, you have D to D transitions that are actually spin forbidden and are also Laporte forbidden. And if you have that instance, those are really difficult to see. And typically you have to use very long path length cells, or you have to make ridiculously large concentrations of those compounds in order to see their electronic transitions. So to kind of put this in perspective as a beginning to this, let's ignore that for now. So if you have, for example, hexaagua titanium 3, this is basically a 3D1 complex, and it's octahedral, and there's 6 water ligands around it. So you can kind of remember that you're going to have this sort of electronic structure in the d orbitals, where that's the HOMO, that's the LUMO, and it's all centered on the d orbitals. And you can imagine that would have an optical transition that would be directly proportional to del O. And if you actually looked at this, it's approximately at 500 nanometers. You can convert nanometers into wave numbers, which then 500 nanometers is 20,000 wave numbers. And that peak is not quite here, but it's like it's about, kind of right there. But you see that there's a peak here and there's a peak here. And then there's another peak down here in the UV. And this sort of starts to tell you something about the nature of transitions, is that it's not as simple as you would think, because you would expect a single transition here, and it would give you a single band, but this band's incredibly broad in terms of energy. And there's actually multiple peaks. In fact, there's a peak, and then this would be considered a peak, and then this would be considered a shoulder. But in general, why is that happening? This one is going to necessarily result from a Jahn-Teller effect in the excited state, which again, we didn't discuss in any kind of detail yet. But you would expect that this should give a single peak, and it really doesn't. So there's more to this than meets the eye, but this is the simplest possible configuration because this is a single electron with no possible repulsion in terms of other electrons that are filling the d orbital set. So this should be an easy example, and it's not so easy. So then let's go to the next example, where let's just look at the energies of this and see what we're thinking. So again, you don't know how to get to these ligand field term symbols yet because we haven't covered any of that yet. But I just want to kind of give you an idea of if you assume that the green photon is absorbed in this molecule, you basically are doing, in essence, a transition that, again, is spin allowed because this is a doublet, that's a doublet, there's only one electron, so 1 + 1 is 2. So you're going from a doublet T2G to a doublet EG configuration. This is the ground state. And then this is the excited state, or should say the first excited state. And ultimately what has happened is that transition took 500 nanometers of photon energy to generate. And then we can convert that into any of your favorite energy units. So you can convert it directly into joules, into electron volts, into kcals per mole, into kilojoules per mole. Just depends on what energy scale you're most interested in. But for our purposes, this is roughly 20,000 reciprocal centimeters. And that's telling you that the ligand field splitting in this particular case is probably somewhere in the vicinity of 20,000 wave numbers. Now that's important information because you can glean insight into the ligand field splitting from the absorption spectrum directly. And like I said, this should be the simplest case, and it's not. So let's go to the one that's a little more involved. And then we're going to have to show you how do you deal with multi-electron configurations, which is going to be the next part of what we discuss in a future video. So again, ignoring where you get the ligand field term symbol from, because we haven't done this yet, now you have a multi-electron configuration. So if you do hexa-agua vanadium 3, this is now 3D2. And that means that you have a ground state configuration here that's effectively a triplet, because remember now we've got 2 + 1 is 3, so that's a ground state triplet. So we know that the superscript in the term symbol is going to be a triplet, but we don't know how to do the rest of it yet. But now I want you to see how multi-electron configurations really now kind of manipulate the absorption spectra. So look at this. Now there's very clearly in the visible part of the spectrum, there are now 2 peaks that are observed. But you would think that, del O should just simply be the transition energy. But then you look at this and you say, well, which transition energy is it? Is it, this electron going up? Is it this electron going up? Like what? Why? And then why are the energies different? It's an octahedral compound. It should have the energy levels exactly as they're shown here. And for some unusual reason, you see 2 absorption bands. And the 2 absorption bands result from the fact that there's multi-electron configurations. This is just only one way of writing a D2 configuration. It turns out if we distributed those electrons across all 5 d orbitals, there are 45 configurations that are possible to write. We'll deal with that later, and we're not going to start doing the D2 configuration. We're going to do something much easier that can be written easily. But the point being is that these multi-configurational electronic states that ultimately are what's governing these observations of multiple bands in a D2 complex is, all going to come back to, we have to start with figuring out atomic term symbols, which are going to be much easier because the d orbitals will be degenerate. It's the same as the free ion term. They're going to be called free ion terms for free ion term symbols, but they're effectively the atomic term symbols that are in effectively the free ion before you impose on it a octahedral ligand field. And then once you impose an octahedral ligand field, you get term symbols that start looking like this, which those are now, the ligand field term symbols. So what we're going to have to start with is that we have to go from the free ion terms and show you how to do that first. Once we do that, then we can go to the next step, to the ligand field term symbols. Okay, thank you for that, for listening to this brief introduction, and I will be back to discuss how do you develop the free ion term symbols for a P2 configuration.